Hello, everyone. Welcome to our final presentation of our senior design project. My name is Ethan Bloomberg. I'll be covering the hardware design aspects of this project.
My name is Monica Rodriguez, and I'll be covering the software aspects of the design.
I'm Yuzhou Zhu. I works on the PID controller design and the manual mode. This is our presentation outline. I will talk about quick overview, PID, and the manual mode. Ethan will talk about hardware design, and Monica will talk about software. Okay, let's start our quick overview. The title of our senior design is Universal Robot Modular Arm, URAM, for mobile platform. Not only our customer, Dr. Lofi, but also our team have the same goal of our senior design. The URAM should be a low-cost, high-torque arm with modular end effector for various ability. For our specific function of URAM, we want to make the arm could keep a vision sensor stable and have the ability to move around the mobile platform, so that in the future, the researcher can easily for the rover reach the function of understanding the environment around the mobile platform for obstacle avoidance by one vision sensor with the help of URA.
Now, I'll be covering the physical design and hardware of our project. To further recap, this is the rover platform that ARM is designed for and its desired range of motion. Projected from the top center, it's a 4-foot diameter sphere with a focus on the sides because this is where the camera will be most useful. And it should carry an Intel depth camera weighing less than 100 grams. We use these target specifications to score and rank various concepts we proposed earlier on, and based on the weighted criteria, the serial joint concept scored the highest and was chosen to proceed. Here we have a standard Revolute manipulator with translational wrist center. The target specifications are used to loosely define our physical parameters, which will be settled on later with prototyping. This led to using point mass approximations to estimate the torque requirements from the arm. This summarizes the key analysis during the design process. We were provided with the motor shown here to use for our project, and from the approximated joint torques, you can see that we would need two of the strongest motors combined at the primary joint to achieve over 12 Newton meters. This would leave us without many motor options for the rotary base and elbow. To solve this, our design uses a differential style joint for its base and shoulder. This type of mechanism uses bevel gears to control both axes while utilizing the motor's combined power to handle 16.8 Newton meters of torque in a single axis. And this is increased to 25 Newton meters with a 1 to 1.5 gear reduction. This would allow simultaneous joint torques over 12 Newton meters. And these are the equations for controlling the gearbox. So here's the rest of the arm. The next two links are extruded aluminum profiles with 3D printed parts to join them. We ended up using one of the weaker motors for the elbow, as our third large MX106 motor was found to be broken. And the spherical wrist was one of the last components to be planned, as so much time went into solving the first three joints, or translational portion of the arm. Since we were already running low on payload capacity, there wasn't a good chance of adding more motors in series, or the time to design a mechanism to move their mass elsewhere. So to save time, weight, and complexity, we settled on using a commercial gimbal for drones. We were able to source the Tero T3D gimbal from the lab, which is 3-axis and designed to hold a camera of roughly the same size as ours. This just needs a couple more printed parts to mount the gimbal to the arm and an adapter to hold our camera in the gimbal. Here's a quick animation of how the arm is assembled. And so during this design process, the arm was also being prototyped and tested in Simulink, The CAD components were imported as file solids to simulate the response of the arm with respect to its physical design and geometry. This includes friction, external disturbances, motor PID controllers, and includes lots of useful measurements like motor torque and end effector error. This helped to determine final link lengths to use for our actual assembly. This video shows the full simulation in action, including a forward and inverse kinematic functions required to control it. Here I'm pulling up the desired X, Y, and Z coordinate inputs to the arm, and you can see the wrist center following the paths. Now move straight along the Y-axis, then the X-axis. Now it goes to its folded configuration, then straight up the Z-axis, back down the Y-axis, where it will end.
From hardware specifications, we move on to software specifications. Beginning with control strategy, the team had to decide on what type of strategy to use for the arm. After some discussion, we had come up with two possible options: task space control strategy or joint space control strategy. When it comes to task space, it can provide smooth end effector motion at the cost of joint jerk and additional logic complexity. In regards to joint space, it provides smooth joint motion but at the cost of end effector jerk. After some deliberation, the team thought it would be best to go for the joint space control strategy for the basis of URMA. Before working with the motors, it is important to understand the material and how to communicate with it. For communication, an Arduino Mini Pro microcontroller is used to manipulate the arms and move the motors to the desired location. Both motors are designed to have 4,095 rotary position, which translates to 0.09 degrees per position. Depending on the rotary position, the motor can move both clockwise or counterclockwise. Knowing that the motors work through serial communication, it is documented that the motors can be daisy-chained with one another to perform simultaneous movement. Lastly, being the MX series, the servo motors can run on two different protocols, Protocol 1.0 and Protocol 2.0. For the use of URMA, Protocol 1.0 will be used. There are two ways that URMA could be controlled, through either manual manipulation with joysticks or automatic manipulation through inverse kinematics. When working with inverse kinematics, it is important that the calculated equations are correct to ensure accurate arm movements. For the calculations, a trigonometric approach was used. Using Python to implement the inverse kinematics for the arm, helpful functions can be used to verify the calculated equations. When calculating θ1, the function math.atan2 was used when the arm was projected onto the xy plane. For the other two angles, they were found when the arm was projected onto the zy plane. After verification, the calculated equations were then implemented into MATLAB. MATLAB was used to simulate how the arm would perform. Looking to the hardware for the software, several materials were key. Due to the proprietary nature of all Dynamixel products, the Dynamixel U2D2 was used to allow USB communication and allow the team to adjust settings of the motors through the Dynamixel Wizard program. As stated before, the Arduino microcontroller was used to manipulate the motors through serial signals. The NVIDIA Jetson holds the higher level logic that outputs rotary positions to the Arduino microcontroller for arm movement. Having the hardware accounted for, software is now necessary. For the lower level logic, the Arduino IDE was used. One key library that was needed was the Arduino master library. This library held a Dynamixel motor.h file, which allowed the use of the motors through Protocol 1.0. For the higher level logic, the API was coded with Python 3.9.6 through the following coding environments: Spider, Notepad++, and Visual Studio 2019. In order to run the logic, a command line terminal was used. For the purpose of URMA, Ubuntu 18.4 LTS was the operating system for the NVIDIA Jetson.
This is the PID controller design part for URMA. In fact, all the motors we used in our senior design have built-in microcontroller. It is hard for us to fully understand their internal structure and find out the transfer function of by them. But both MX-28 and MX-106 are DC servo motors, and we usually consider the system of DC motor is a second-order system. Therefore, in order to find out their rough open-loop transfer function, firstly, we need to collect the count data from the servo motors. And this task could be figured out by Dynamic Soul Wizard 2.0. It can output the sampling graph and the CSV file about count data of each servo motor. Then we use system identification from MATLAB to analyze this data and get the rough transfer function. According to the datasheet of each kind of servo motors, we get the relationship between Kp, Ki, Kd, and PID gain. It is very important for us to set and tune the PID controller. Now, let me show the rough second-order transfer function with load of each kind of servo motor. For MX-28, the load is the arm for MX-28 in URMA directly. And for MX-106, according to the calculation of the hardware design, we sample the count data of MX-106 with 1 Newton meter. Discrete time tuning way usually gets a better behavior for system. So while we design and tune the PID for motors with load, we use the data from discrete time tuning way. This is the graph. This is the simulate graph of MX-28, and this is the simulate graph of MX-106. Our PID design goal is to remove the steady state error, minimize overshoot as possible, and improve the response speed appropriately. Now we get the PID gain of MX-106 and MX-28. And we set off this date, verify and compare the behavior between original sampling graph and sampling graph with PID controller. This is the comparison of MX-128, and this is the comparison of MX-106. It is easy to find out that with the help of PID controller, the behavior of each motors improves a lot. Finally, I combine them together to check the total steady state error and overshoot of the whole system. According to the simulation graph on the right, we can see that the behavior of the whole system is stable and accurate enough for URMA. Now we get everything ready. This is the final part of our presentation. Let me show the demo video of modular mode. This mode, we use joysticks to control the whole system. Before writing the code, the torque limit and the PID gain has been set by Dynamic Soul Wizard. We use the Arduino Mini Pro as the controller for manual mode. With the help of the library Dynamic Soul Motor, we could easily change the position of each servo motors by cord and joysticks. Meanwhile, we changed the angle of the Gamble by PWM. The overall goal of the team was to design and build a multipurpose modular and effector robotic arm for the use of research. In the end, a multipurpose modular and effector robotic arm was made, so it can be only controlled through joysticks and not through inverse kinematics as originally intended. It can still perform most of the functions that we started previously. When working with the arm, it is shown that it can perform accurately and still be strong and stable. Meanwhile, the low cost is reflected in all aspects. Used servo motors were recycled from an abandoned arm to build URMA, which reduced the cost of the arm greatly. In regards to the objective, the researcher can easily reach the function of understanding the environment around the mobile platform and obstacle avoidance with only one vision sensor in the future, which could also reduce the future cost for research and development.
So, in conclusion, I'm proud of our project. I think this was a great task to learn many key aspects from our curriculum. And while any one part of our project would require a deeper dive into its specific subject, I think this was a great product to demonstrate the wide breadth of mechatronics. While I'm not fully satisfied with our end product, I'm confident that we made a positive contribution to the platform's research project. Regardless of the final implementation, we're able to successfully design and manufacture a robust manipulator. This will be a great start for any future students or researchers working to improve or build on the project.
Overall, if the traditional time frame of 32 weeks is still on the table, I foresee that it would have been a feasible feat to have all the goals met for the project. Considering that the team only had 14 weeks and produced a working product, that is considered an amazing accomplishment, as it is the first time MRE 480 and 481 are offered in the summer. After having the experience of creating a robotic product for user consumption, there were many lessons that could be taken away. Seeing firsthand how quickly things can both develop and deteriorate, having ample time, strong lines of communication, determination, and the ability to adapt are key goals to have for a successful project. Furthermore, now having a taste of what is to come for our professional lives, it gives each individual involved an idea of what is to expect in the future, which also includes expecting the unexpected.
Finally, thanks so much for everyone's help for our senior design.